Welcome to the Intel Quartus Prime Software Design Series, Timing Analysis Online Training Part 3, Clock Constraints. My name is Steve. In this course, I will go over the creation of base and generated clocks, along with clock uncertainty and clock groups. Here are the recommended prerequisites for this course. An online training called Timing Analyzer, Introduction to Timing Analysis, that can be found on the Intel FPGA YouTube channel or on the Intel FPGA Trading website. Knowledge of FPGA architecture and the design flow, and familiarity with the Intel Quartus Prime Pro software. If you haven't done so already, check out our previous courses listed here in this series of online trainings. Constraining your design tells the software tools your desired timing goals so that the fitter and timing analyzer can properly report back if your design can properly operate with the timing requirements. To constrain your design, you'll need to understand the timing of the system environment, such as the board delays and time requirements of the other components connected to your FPGA. What if your SDC file is not exactly right, or some constraints are off by a little bit, or some constraints are missing? It probably does not sound like too big of a deal, but these incorrect or missing constraints can cause the fitter to make incorrect optimization choices and potentially spend too much time trying to reach timing closure in certain areas of your design where timing is more restrictive than necessary. And when the fitter works unnecessarily hard, then other areas of the design will suffer as a result. Not only will the fitter spend time on unneeded constraints, but the timing analyzer will spend time processing the incorrect constraints. This course is about writing SDC files for common Intel FPGA design situations. For questions about writing SDC, refer to these user guides and online helps. And there is the tickle and command line help as well. I point out the tickle and command line help because they are installed with the Intel Quartus Prime. When you're in the Intel Quartus Prime user interface, and you want a quick reference for a particular command, such as what are the arguments for a certain SDC constraint, if you're in the tickle console in Quartus or in the console in the timing analyzer, you will notice a question mark at the left side of the slide. Click on the question mark, and that will open the command line and tickle API help GUI as shown. It is basically the reference guide for anything scripting. Highlighted here are the SDC and extended SDC commands. The SDC section are all the standard SDC commands from the SDC specification, and the extended SDC are commands that Intel has added. In this course, I will focus on writing SDC constraints. The clock constraints are always a good starting point for SDC files. Once all the clocks have been properly defined for your design, then all or nearly all the design's paths are completely defined. In this section, I'm going to go over the more common types of clock constraints, namely base, generated, and PLL clocks, clock uncertainty, and clock groups. What is a clock? In SDC, a clock is a signal property that describes a waveform and is attached to a design location that is referred to as a target. The target is generally ports or pins of registers and keepers. When you create a clock in SDC, you end up creating a clock domain so that every register that is attached to the defined clock is now part of that clock domain. All timing analysis is based on the launching clock edge to the latching clock edge. Two different types of clocks are the clock and the generated clock. The clock could also be called the base clock, and its phase and frequency is always as you describe it and not dependent on any other defined clock. The generated clock, or derived clock, will be based on another clock that could be a base clock or another generated clock. The generated clock's properties will be dependent on the clock from which it was derived. A good example of generated clocks are the output clocks from a PLL. The command to create base clocks is the create clock SDC command. Use this command with the arguments to describe the waveform of your clock signal. I will now go over some of the more common arguments used for the create clock command. Any argument you see that is listed in square brackets means that that argument is optional, but there are some exceptions that I will point out. The name argument will associate this clock domain with that given name. If the name argument is omitted, then the clock domain's name will be the same name that is referenced in the target argument. The period is a period in nanoseconds, but you can also give the period in hertz if you like. You could specify the properties of the waveform if you need something more than the default of the rise time that starts at 0 and the fall time at half the clock period, such as a shifted clock or clock that has a non-50-50 duty cycle. The target is the point in the FPGA that will be used as the source of the clock. Usually, the target is applied to ports, pins, registers, keepers, or nets. The add argument allows you to apply multiple clocks to the same target without overriding previously added clock constraints, and each additional clock constraint will be used in all of the analyses. Without the add parameter, then the default behavior is a clock assigned to the same point in the FPGA with the same name that will overwrite the existing clock. A clock assigned to the same point but with different names will be ignored and the previously created clock will be used. In the top example, I am creating a base clock with frequency of 50 MHz, so the SDC command is create clock with the period argument of 20 nanoseconds, and the clock domain name is clock50. I am targeting the clock import by using the getPorts collection command. I did not specify any rising or falling edge times, so the defaults of a 50-50 duty cycle are used, which are the first rising edge starting at 0 nanoseconds and the first falling edge starting at 10 nanoseconds. This clock that I created will repeat every 20 nanoseconds as noted by the period. While the name of the clock in the design at the port is clock in, the name that will appear in all the time reports will be clock50. The second SDC command example specifies a 100 MHz period with a 60-40 duty cycle, meaning the time that the clock is high 60% of the time. The clock is also phase shifted by 2 nanoseconds. The duty cycle and the phase shift are noted in the waveform argument, where the first number is the first time for the rising edge time and the second number is the first time for the falling edge time. This command is being applied to the port sysclock, but I'm not defining the name, so the clock domain name will take on the target of the create clock command, which is sysclock. Here's the GUI dialog box for the create clock SDC command. As you fill in all of the parameters in the GUI, the SDC command field automatically fills in. Note the target's data entry field. You can simplify finding the targets by using the name finder, which allows you to parse through the database to find the clock argument that you are interested in. The next clock constraint that I'll talk about is the create generated clock. This command is used to create a clock that is internally generated in the FPGA. A common example of internally generated clock is a clock coming from a PLL. This command tells the tools to look at a source of the clock and then modify the source in some fashion, such as phase shifting, increasing or decreasing the frequency, and so forth. There's also no need to try to figure out the clock propagation delays to the point of the generated clock, as the tools will automatically use the timing numbers generated from the fitter, so you create this generated clock for the ideal scenario. The name, target, and add arguments for the create generated clock work in the same way as the create clock command. The notable difference is the source, which is the only required argument for the create clock command. The source is the point in the design that is the reference for the generated clock. The source has to be a port, pin, register, keeper, or net object type. It is recommended that the source is also the target of an SDC command, but it's not required. The master clock argument is used in the event that there are multiple clock domains at the source, since the create clock command also has the ability to add additional clock domains. The arguments listed on this slide further manipulate the source clock by dividing, multiplying, applying a duty cycle, inverting, setting an offset time, or applying a phase shift. Here's a screenshot of the Create Generated Clock GUI. All the command line arguments are available as data entry fields, and once the fields have a value, the SDC command field at the bottom automatically gets updated to adjust for the current options filled in and selected. Here's an example of generated clock. It is a simple clock divider where the output of the flip-flop drives an inverter, and the output of the inverter drives the D-input of the flip-flop. The flip-flop's clock will be used as the source for the Create Generated Clock command, and the target of the command is the register called inst. This circuit creates a clock that is half the frequency of the source clock at the Q output. So, for the SDC commands, I create a base clock of 100 MHz targeting clock in, and the clock domain name will be the same name as the target, clock in. I then create a generated clock, creating a clock domain name of clock div, and then target the Q output of the flip-flop, and use the clock in as the source and the divide by 2 argument to describe the frequency of the generated clock. The generated clock will have a frequency of 50 MHz. Here is the same example as what was shown on the previous slide, but using the collection get pins to grab the clock pin of the cell named inst, rather than get ports collection grabbing the clock import of the Create Generated Clock command. Because of this slightly different way to write the constraint, the Create Generated Clock command will capture the clock properties of any different clock port that connects to the clock pin of the D flip-flop that is used, since the source is the clock pin rather than the clock port of the design. Also note that the target is the Q pin of the cell named inst. Then finally the result is the same, namely that you end up with a generated clock that is half the frequency of the source clock. Here's another example using the Create Generated Clock command. This circuit has a 200 MHz clock that is driving a couple of clock dividers. The registers div clock and div clock n generate clocks with a frequency half of that of the system clock. Register div clock has its clear port attached, so this register will start out low. Register div clock n has its set port attached, so it will start off high. Both registers have a Create Generated Clock command associated with them. Notice that the second Create Generated Clock command uses the invert argument to accommodate the set port being used instead of the clear port. Most FPGA designs make use of the available PLLs. In most cases, you need to create a PLL type IP, and in doing so, you specify the parameters that you need from the PLL, namely the reference clock and the output clocks. Tools will then create an SDC file associated with that PLL IP. While the Intel Agilex and Intel Stratix 10 FPGAs have automatic constraint generation for the PLLs, older device families could rely on the Derived PLL Clocks to extract the PLL's clock information for use in timing analysis. To help with the SDC constraints and have recognizable names rather than machine-generated names, you can enter parameters to name the SDC objects for the IOPLLIP. When creating an IOPLLIP, you need to enter reference clock frequency that will be used as part of the constraint. And in the output clock section of the IP creation, you have the option to name the clock domain name so that you can have a recognizable name to use rather than a machine-generated name. Select Give Clocks Global Names and fill in the clock name field to name this output clock. And of course, don't forget to fill in the desired output frequency. With the clock domain name created for the IOPLLIP, you can see in the Timing Analyze report that the 100 and 200 MHz output clocks are easily recognized because of the names entered when creating the IP. Not entering the names will give you clock domain names based on the hierarchy of the IP as shown for the last 2 clock names. So, for Agilex and Stratix 10, you don't need any PLL constraints in the SDC file. The clock constraints are automatically created from the input reference clock and all output clocks based on the PLL settings. Here's an example SDC file that was automatically created for a PLL IP. Notice the PLL reference clock is properly constrained and there is a generated clock for each of the PLL's output clocks. For each of the output clocks, where the designer specified a clock name, the name parameter was used, making these output clocks easily seen in the timing analysis reports that get generated. There could be some use cases where you need to override the PLL's automatically generated SDC constraints, such as the input clock to the PLL will change, but the parameters of the PLL will be unchanged. The design has a means to change the PLL settings, or the auto-generated names for the PLL constraints are cumbersome to work with. In each of the use cases described, you can manually enter in the desired constraints into the SDC file to override the constraint that was automatically created for the IP. When overriding the constraints, be sure to place your SDC above the IP's SDC and Timing Analyzer's SDC file list. For the older device families, there is the Derived PLL Clocks SDC command. This command tells the software to examine the PLL parameters and create generated clocks on the outputs of the PLLs. The create base clock argument will also take the reference clock parameter of the PLL IP and create a clock on the input to the PLL. However, using the create base clock argument does not override any clock constraint that has been added. The Derived PLL Clocks along with the create base clocks argument will happen automatically in the software if there are no other clocks defined in the SDC file. But if you have defined clocks in your SDC file, which you should do, then you will also need to manually add the Derived PLL Clocks command. Here's the GUI dialog box for the Derived PLL Clocks when you invoke the GUI to insert the constraint into your design. Here are some examples on creating clocks for EPLL. In the first example, I use the Derived PLL Clocks with the create base clocks switch so that the tools will extract the input and output clock information from the PLL IP. In the second example, I create a clock and then use the Derived PLL Clocks without the create base clock since it would be redundant to use both the create clock and create base clocks. The third example shows what the standard SDC commands of create clock and create generated clocks would be without using the Derived PLL Clocks. The SDC clock uncertainty allows you to create a clock with irregularities in the waveform such as jitter and skew. When you account for the uncertainties in the clock waveform, you increase the accuracy of the timing analysis, and as such, you reduce the margins for the setup and hold analysis. The effect of accounting for uncertainty is accounting for the non-ideal situations of your clock. The shaded areas in the clock waveform on the bottom show how including the jitter can lead to a better analysis for the hold times and setup times. While the timing might be more difficult to reach, you'll end up with a better performing design in your FPGA as a result. There are clock uncertainties that are inherent with the FPGAs. These values have already been calculated and included with the FPGA's timing dataset. Therefore, the software tools will automatically run the derived clock uncertainty command to ensure that the clock variances are accounted for, so you do not need to add these inherent uncertainties to your SDC file. If you are curious about the uncertainties, you can see the values by running the report SDC command after place and route has finished. While the tools will automatically run the derived clock uncertainty command, you can still set clock uncertainty to account for your off-chip clock and to create a guard band to your existing clock. The guard band method is a way to over-constrain your clock without changing the clock's frequency. Here is the set clock uncertainty command that you use to add your own uncertainty or skew. The arguments for the set clock uncertainty command are as follows. There's the value of the uncertainty that you are adding. There's the add switch that allows you to add your value to the automatically included value rather than just replacing the inherent value. You're allowed one add per clock domain. The from switch specifies the originating clock domain. The to switch specifies the destination clock domain. The setup switch specifies that the uncertainty value is specifically for setup analysis instead of the default of setup and hold analysis, and likewise for the hold switch. And here's the dialog box allowing you to create the set clock uncertainty command through the GUI. In the first example, there is an uncertainty value of 0.7 nanoseconds that will be added to any intrinsic FPGA value. Since neither setup nor hold were specified, the 0.7 nanoseconds value will get divided by 2 in the SDC command so that the value gets split evenly between the setup and hold uncertainty times, resulting in 0.35 nanosecond increase in the setup and hold time requirements. In the second example, the uncertainty value is applied only to the setup uncertainty and is also added to the inherent value in the FPGA. The SDC specification states that, by default, all clocks are related. So, unless explicitly defined, all clocks' rising edge starts at time 0. What this means is that all parts of your design that interact together, even if they are in different clock domains, will be analyzed using the smallest positive launch to latch edge relationship. Data transfers between clock domains using the smallest positive launch to latch relationship, which might be 0.2 nanoseconds, may need to have those paths cut from being analyzed and other constraints added to make appropriate accommodations. To help with proper analysis between clock domains, there is the setClockGroups SDC command. This command defines which clocks are related and which ones are not. All paths between the selected clock domains are ignored. Within a single setClockGroups command, all related clock domains are listed in a single group argument. You can use as many group arguments as needed, each with its own list of clock domains, so that each group's list's clock domains are unrelated to every other clock group's lists. After you have set up your clock groups, you need to specify whether the clock groups are asynchronous to each other, internally muxed with the logically exclusive argument, or externally muxed with the physically exclusive argument. You want to use setClockGroups for the analysis to tell Time Analyzer which clock domains are not related. One of the arguments, asynchronous, logically exclusive, or physically exclusive, has to be used, and a clock can appear in only one group argument for a single setClockGroups command. Use as many groups with a single setClockGroups command to define relationships between those clocks. When you use one group argument with its list of clocks, the clocks in that list will all be related, but all the other clocks in the design will be unrelated to the clocks in the group list. Any clock domain not listed in a group will still be treated as related to all of the other clocks not listed in the group. Here is the dialog box associated with the setClockGroups command. Type in the arguments in the field shown, and as you do that, the SDC command field gets updated. Here's an example of an external clock mux. I'm creating two clock domains, a clock 100 for the 100 MHz clock and a clock 66 for the 66 MHz clock. The clock switching is done outside the FPGA, so the physically exclusive switch can be used since their separation is physical. The output of the mux is driving the clock port, so I use the -add switch when creating my clocks, since both clocks will target the same source. I use two group arguments. One argument contains the clock 100 domain, and the other argument contains the clock 66 domain, so that no analysis is done between the two clocks. In this example, I have two clocks in the design, so my createClock commands do not need the -add argument, since each command targets a different port as its source. However, I do need to use the createGenerated_clocks command because of the internal muxing of the clocks. I'll have two createGenerated clocks targeting the same output pin of the mux, so I need to include the -add argument on the second createGenerated clock. Next, I will use the setClockGroups command using the logically exclusive switch since the clocks are internally multiplexed. I'll use the group arguments twice, one for each clock domain, so the Time Analyzer will know that the clocks are not related. Here are a couple of examples showing the impact of using the group argument in a couple of different ways. At the top, I have listed all of my clocks for my design. In the example on the left, I have a single setClockGroups command with two group arguments being used. Notice that clock E is not included in any of the groups. In the first group, I have clock A and clock B, which tells Time Analyzer that those two clocks are related, and the second group has clocks C and D. Clocks A and B will be analyzed together, clock C and D will be analyzed together, and clock E will be analyzed with every clock. In the example right, I have two setClockGroups with each command using only one group argument, resulting in clocks A and B getting analyzed together, and clock C and D getting analyzed together, and clock E getting analyzed by itself. Now that you've entered in all the timing constraints for your design, you want to make sure that everything is working as you expect. At this point, you only need to let the fitter run to the plan stage and open up Timing Analyzer to make sure all your SDC commands are good. The list on this slide are the reports you should generate to make sure your design is properly constrained. Report clocks will report all clocks that are defined, whether they are created automatically or from your SDC. Use this to check and make sure that the parameters look right according to your understanding, such as the clock frequency, names that come from the PLL settings, the duty cycle, inversion, and so forth. The report clock waveforms generates a report so that you can visually inspect the relationships that the clocks have with each other and that the clock edges line up the way that they should. In this report example, you'll notice that at time 0, all the clocks start their rising edge, which is the default behavior. The visual inspection is nice because you can check to make sure if any of the clock paths should be cut from other clock paths just by noticing if the rising edges of different clocks are not exactly aligned with another. Report clock hierarchy shows you the same information as report clocks, but arranges the information hierarchically. You can see the base clocks and then all the generated clocks from the base clocks. This helps you verify the relationships between clocks and how they are related. Report unconstrained paths will tell you what kind and how many paths in your design are unconstrained. The report also notifies you which signals the software considers as clocks that you have not defined. Report SDC will list all the constraints that are currently applied to your design's netlist. What is shown here is the clock uncertainty, which includes the automatic and any additional clock uncertainty that you added to your SDC file. Notice the source column in the screenshot that it shows you the line number in the SDC file where the command came from. The report clock transfers report lists setup, hold, recovery, and removal path counts for all clock-to-clock transfers in the design. The report displays all possible transfers going from rising to falling and all combinations thereof. If a path exists in the design, the report column cell is white and lists the number of paths. If a path is a false path, the report column cell is light gray and contains the text false path. If a path does not exist in the design, then the report column cell is dark gray. The clock pair classification lists intraclock transfers where the from clock and to clock are the same, interclock transfers where the from and to clocks have a known phase and frequency relationship, asynchronous where the from and to clock are asynchronous and the paths between these two clocks have not been cut from analysis, but they probably should be cut. The ignored clock pair classification means that the relationship between the from and to clocks have been cut and will not be analyzed. The report CDC Viewer gives you a two-dimensional graphical representation of your clocks in your design. The relationship between the paths are color-coded for easy reference. Each square will give information about the two clocks, such as the slack and total paths between the two clocks. You can also expand the clocks to reveal any associated hierarchy. You can right-click on the squares in the report to apply constraints for the clock crossing. To summarize, in this course, I went over the creation of base and generated clocks, along with clock uncertainty and clock groups. This concludes part 3 of a 5-part series. I encourage you to check out parts 1 and 2 if you haven't done so already, along with parts 4 and 5 of this series listed here. There are many ways to get training about Intel FPGAs. You can watch hundreds of videos on our Intel FPGA YouTube channel, register for our e-learning classes on our Intel FPGA training website, or enroll in one of our regularly scheduled instructor-led online classes. Not only do we have quality classes, but they are also free of charge. If you still have questions about our FPGA products, visit our online forums. One more thing. We are always looking for ways to improve our training. Send us an email with your feedback about the course that you attended. My name is Steve, and thank you for listening to this course.